All right, everybody. Welcome back to office hours. I'm so sorry about the little delay we had going on today. Literally, maintenance just decided to show up and do all the carpets and stuff. So, kind of detour we took. All right, so we're just gonna do some two critical thinking problems to finish up our radical topics. So we're gonna do 11 and 12 on page 98 and 99 of the student workbook, and then we're gonna go into all the nucleophilic substitution and beta elimination reactions. Okay, so look at number 11 right here. So we see provided below is a reaction coordinated diagram for allylic bromination. Okay, and this is kind of the reaction scheme over here. And they want to know what is our main intermediate at position A. So, this reaction, in the initiation step is going to form, a radical on this, N-bromosuccinimide. This is going to homolytically cleave such that we form a bromide radical and then this kind of amide radical. So essentially, we know we did our initiation step, we have that bromide radical, and then our intermediates would be the results of these propagation steps. So in terms of initiation and termination, those wouldn't be intermediates, but those propagation structures are definitely going to be our intermediates. So, what necessarily happens when we have, I'll put this up, what necessarily happens when we have the structure, and the structure is that we have kind of this weak bond over here. And what happens is we can abstract a proton to get to this tertiary allylic radical. Okay, so that's the radical that forms first, okay? But is there a more stable position that could potentially go through some sort of rearrangement? Yeah, well, remember, we can take one electron from that pi bond, take one electron there, and put this electron back on that allylic carbon. And essentially, we change the substitution pattern of the alkene to a tri-substitute alkene, and we get the radical now on a secondary position. So this would definitely be the intermediate at position A. This is our main intermediate at A. B, draw the major stereoisomer that results from this reaction at position B. So you're going to get a bromine at that position. So for B, you're going to get a structure that looks like this. So remember that radical is an sp2 center, has an unhybridized p orbital, so we can attack either from the front face or the back face. Okay. And C, what does the energy barrier refer to? Okay, so what is the energy barrier required to homolytically cleave a bond? That should ring some bells. It's bond dissociation enthalpy. Okay, the bond dissociation enthalpy. So BDE. Okay, it's the amount of energy required to homolytically cleave that bond to get to that stuff. All right, that's 11. Any questions? All right, let's go to 12. So 12 is kind of just rationalizing BDE, radical stability, bond strength, all those kind of terms together. So here we have this BDE plot with 4 distinct energy levels, not necessarily drawn to scale, but just 4 different energy levels. And here we have all these bonds in bold, HA, HB, HC, HG. So the first thing is, let's kind of plot these. So if I were to homolytically cleave HA, I would get a secondary radical. If I were to homolytically cleave HB, I would get a secondary radical, but it's destabilized via induction with that carbonyl group. And then over here, we would have a tertiary allylic radical. So this would be tertiary allylic. Maybe I'll write that, tertiary allylic. And over here, you would get secondary allylic. Okay. So overall, these would be my classifications. Secondary induction, secondary allylic, tertiary allylic. That should be enough to rationalize where these go on the energy plot. So if it's going to form a more stable radical, that BDE is going to be really low because it's a stable product. So HD would be the most stable product, so it has a relatively low energy barrier to get there. Then that secondary allylic, which would be HC, would go next. Then that plain secondary would be after that, HA. And then finally, HB, because it's destabilized via that inductive group. Okay, so for A, B, C, and D, we're just going to answer these questions based on this bond. So the proton with the greatest bond strength. So the proton with the greatest bond strength is the one that is going to form the weakest radical. Okay, it has the greatest bond strength because if I were to, break that bond, it forms a very, very unstable product. So that's not what we want. So this would be HB. Okay. The proton with the weakest bond strength is the one that forms the most stable radical. it's the weakest bond because it forms a really stable product, HD. Okay, and the shortest carbon-hydrogen bond implies the strongest bond, so that would parallel letter A, so that's HB. And the longest carbon-hydrogen bond indicates it's weak, so that would be HD. All right, so this is a really good question in terms of rationalizing, relative energies, using these terms in terms of bond strength and bond length. This is a kind of big picture item here. I would definitely know to do that. Any questions on any of the radical reactions? I know Dr. Peterson sent out an announcement, going over the elimination, but I think we covered that pretty okay. Alrighty, so today I'm gonna start doing some chapter 9 material. So we're gonna do nucleophilic substitution. And honestly, this is the hardest chapter in all of organic. I even find it the hardest chapter in organic 1 and organic 2, to be completely honest. It's just like, you have these 4 kind of umbrella items here. You have these 4 umbrella reactions, Sn1, Sn2, E1, and E2, and it's up to you to determine, which mechanistic pathway that reaction is going to follow. So why is this the case? Why do we have 4 categories and it depends on a whole bunch of factors? Well, we have this argument here. So let me show you the structure. So, this is just, let's just say a plain haloalkane. It's a tertiary haloalkane. And I'm going to just subject this to like some sort of solvent. So let me just say methanol. So this is methanol. It's both my reagent and my solvent. So this is a specific reaction called solvolysis, where your solvent acts as your main reagent. And what happens here is, in the rate determining step, we could argue that, potentially this, bromine would leave on its own, and we form this tertiary, carbocation. And then, maybe that methanol could come and attack here, okay? And in doing so, and maybe a few steps later with deprotonating, you would get this kind of methoxy group, so we added this ether onto the starting material. But at the same time, let's go, do the same thing here, and let's say I have that same intermediate, and I have that methanol, but methanol could also do this. Take off a proton and donate that electron density into, that carbon deficiency to form a pi bond, okay? So you see the exact same intermediates here, the exact same reagents here, but 2 very different mechanistic pathways. Here, it looks like that oxygen acted as a nucleophile to form a new carbon-oxygen bond, but here, oxygen's acting as a base to deprotonate, that proton and fix that deficiency by forming a pi bond, okay? So this is kind of like the reason why we have these umbrella reactions, is because it depends on the conditions. You can argue, you can promote, this pathway, let's call, this one on top, pathway A, and pathway B, and you could, arguably like control one pathway to, form more of one product or form more of the other product by, changing, the substitution of my starting material or changing my reaction conditions. And that's kind of what we're going to see is, how do I know when to form this? How do I know when to do that? And so forth and so on. Okay. So that's kind of like the logic I like to show. Why do we have all these different things going on? And I think that makes sense at this point. Okay. So let me just briefly go over Sn1 and Sn2 and E1 and E2. So let's start with Sn2 first. So Sn2 is the easiest to understand. So Sn2, we're going to read this backwards. So it's 2 meaning bimolecular, N meaning nucleophilic, and S meaning substitution. So this reaction is called a bimolecular nucleophilic substitution reaction. Bimolecular is basically going to tell me that I'm dependent on 2 starting materials. Okay, so my rate law is going to have 2 things in it. So bimolecular, if you remember kinetics back to Gen Chem, means that my rate law is dependent, so is directly related to, that's what that alpha symbol means. Rate law is directly related to 2 reagents. So, okay, so how fast this reaction progresses depends on 2 things, not 1. Okay, so what does that look like? Well, it's going to be something like this. I have, this haloalkane, and I have some really good nucleophile. Maybe let's just do something like this, sodium azide. Okay. And, some sort of solvent like DMSO. Okay, something like that. So let's talk about this. This is an example of an Sn2 reaction. So some things to notice is that we have a really, really strong nucleophile. How do I know it's a strong nucleophile? Well, anytime there's a complete negative charge on something, like anytime, it's a really, really strong nucleophile, okay? Unless it's bulky, which we'll talk about later. So anytime I see a complete negative charge on something, it means that it has a lot of electrons to donate, you know, and react with something. So this means this negative charge indicates strong nucleophile. And strong nucleophiles like to attack, you know, electrophiles. So we know that this reagent is an electrophile, okay, because of that halogen bond. And what is this DMSO? So DMSO stands for dimethyl sulfoxide. Okay, so I actually use this a lot in my orgo lab, you know, when I'm doing certain like reaction conditions, reaction tests and stuff. So this is dimethyl sulfoxide, and all of these protons, okay, all these protons are not acidic, really. None of these are really acidic. So their pKa's are like greater than 25 or something like that. pKa is greater than 25. So really, really high pKa, which means that they're not acidic. So none of these protons are going to exchange with that azide. So what we don't want to happen is this. We don't want that azide, the negative charge, to grab a proton. Because if it does that, then we form HN3, which is no longer a nucleophile, no longer a strong nucleophile, okay? So we don't want this, okay? We don't want these strong nucleophiles to grab protons, like in water, for example, or like an acidic solution, for example, because then you lose this nucleophilic property of that, you know, reagent. So something that we're going to talk about here is we have polar aprotic solvents. Okay, polar aprotic, so something that doesn't have protons, and I think that kind of makes sense now. We don't want these nucleophiles to get these protons because then they lose that nucleophilic property. Okay, and then another feature that we have is, notice how this center is really sterically unhindered. So this position is really only a primary, you know, primary haloalkane. So, you know, we tend to react with very unsubstituted, or, you know, maybe let me say better, sterically unhindered carbons, okay? So like a primary or a secondary, something like that, okay? So that's really all you need to know for an Sn2 reaction. We have, you know, this bimolecular nucleophilic substitution reaction, which is dependent on two things, the haloalkane starting material and your reagent. Also, notice we have a polar aprotic solvent because it just improves the nucleophilicity of that azide, you know, nucleophile. And I think that's it, right? So far, and we're also, you know, limited to these sterically unhindered carbons for a reason that I'll talk about in a second. So mechanistically, I'll redraw this down here. Mechanistically, what's happening is that azide is going to attack this carbon, and, you know, this carbon-bromine bond is going to break for reasons we've already discussed. That halogen is very electronegative. It's going to retain that electron density. So the resulting structure is just azide, right where that bromide, you know, used to be. Okay. So, you know, this reaction is pretty, you know, self-explanatory so far, but, you know, let's look at a secondary example, you know, maybe something that's a little bit more ambiguous. So another example of an Sn2 condition could be, let's say maybe, we'll do something like this.
Can you scoot it down, please?
Yes, sorry about that.
Thanks.
Yep. Okay, so let's just do something like this. So, you know, we have this water, looks like it used to be an alcohol, and it looks like it got protonated, and it looks like it's water now. So that means it's a very good leaving group. You know, the fact that this, you know, water molecule is protonated, you know, we know water exists on its own. Like, it's a big indicator that this group wants to leave. Okay, so, you know, secondary, you know, reagents are a little bit more ambiguous in the sense that we don't necessarily know if they're Sn1 or Sn2 conditions. What determines if it's Sn1 or Sn2 when we're dealing with secondary things is the specific reagents. So again, if we want Sn2 conditions, we want what? We want strong nucleophile, which is reassured by having that polar aprotic solvent. So let me just do like that same example, sodium azide. Okay, so if I were to dissociate those two ions, it's positive and negative. And let me pick a different, you know, polar aprotic solvent. So maybe let me do acetonitrile. Okay, so acetonitrile looks like this. So it's literally an acetyl group, CH3, and the nitrile functional group. Okay, so I've worked with that as well, acetonitrile. So essentially, what is the stereochemical consequence from this? And why are in Sn2 conditions are we limited to these very sterically unhindered starting materials? And the reason that is same reason that we saw, with those rings, with those Helenium bridges, is that this wedge, orientation limits that front face of the carbon from being attacked. So the only other possibility is that azide to come in on a dash and attack that carbon to promote the removal of that water. So we would expect inversion of that stereochemical configuration. So we would get that azide on a dash instead of on a wedge. Okay, so that's just a stereochemical consequence. So, and to verify that, we could see that we go from 1, 2, 3. So we're going from, an S chiral center to over here, we're going to 1, 2, 3 to an R chiral center. Okay, so we can even verify using Angled prelog rules that these stereocenters, in fact, inverted their absolute configurations. Okay, so some other key details to note about Sn2 conditions is that the specific transition state, this is like really not that important, but if I were to draw, this transition state, it does something like this. Let's just say this is my nucleophile, and this is my, I'm just gonna say, let me do this, R, maybe here, and here, let me just call this like leaving group or something, and I'll call that R, R1, maybe R2, I don't know, something like this. And essentially what happens is that nucleophile is going to attack here, and that's going to leave, okay? So this is my transition state. But notice that this specific geometry has a name, okay? So this is called the trigonal bipyramidal geometry. Trigonal bipyramidal, I totally spelled that wrong, but whatever. Trigonal bipyramidal geometry. So essentially, what does that mean? Trigonal meaning this is a triangle. If you can see, this is kind of like a triangle. And there's 2 bipyramids. There's this kind of point to the pyramid, and then this kind of point to the pyramid. So it's up there and up there. So trigonal bipyramidal geometry, specifically for Sn2. And you see how, these wedges and dashes are associated here. They actually get forced over to the other orientation where, now we may have the R2 and R1 here with the nucleophile here and, R here, whereas before it could have been like this. So, based on the actual connectivity of these things, they're not the same. So you can see that R2 is on the left here, R2 is on the right here. That's a result of this nucleophile forcing those substituents to switch configuration. That's just like that's a little specific. I mean, the only thing I would really want to know about this is that transition state for Sn2 conditions follows this trigonal bipyramidal geometry condition. Does anybody have any questions on Sn2? Because that's kind of all I got so far for that.
I have a question.
Sure.
It's kind of stupid, but what's the definition of protic and then aprotic?
Solvent?
Solvent, yeah.
Okay, cool. Good question. So that's not stupid at all. Actually, that's kind of like the big kind of takeaway here is that protic solvents are things like water. So that's actually a great question. Protic and aprotic. So protic things would be like water. Okay, so these have these protic, it means proton. Like aprotic means without protons. That's kind of where that word comes from. So, anything like, this, like that's carboxyl, that's acetic acid. So water, acetic acid, these all have these protons, like I don't even know, like even methanol, like all of these are protic solvents because they have these protons that can exchange with things in solution. Okay, so aprotic things would be like DMSO. Okay, and you're gonna see these like, they're the same, I guess, 5 of them. I can't really think. Acetonitrile, I think THF is one of them. Like they get these special names, okay? And some examples, like I'll show DMSO, which we saw earlier was, DMSO, it looks like that. DMF is, I forget what DMF structure is, but I know acetonitrile is this. THF is that, okay? And yes, they have protons. Yes, they do. Like, I'm not saying they don't. But all of these protons are not acidic enough to exchange in solution, okay? So that's kind of the difference here, is that protic solvents have all these protons that can, exchange in solution, and aprotic don't necessarily have these acidic protons. But what does that really mean for the nucleophile? That's really what it matters, is what do these solvents effects have on the nucleophile? So let's take the same thing. Let's take, let me do hydroxide for this example. Let me take this hydroxide, nucleophile, good nucleophile, also a good base, and that's the problem, is that good nucleophiles are also good bases, typically. So good nucleophile typically equals good base. Okay, so we know bases like protons. So if I want to do an Sn2 reaction, which stands for nucleophilic substitution, okay? If I want to do that nucleophile, adding into something and using those nucleophilic properties, I need to make sure I'm using this aprotic solvent. Why specifically that aprotic solvent? It's because when, let's just use DMSO as an example, these are all the DMSO molecules hanging out in solution around that hydroxide. And notice nothing is really complexing with it because it's not protic. We're not losing protons. There's no kind of solvation of that hydroxide. Okay, but let's take, a protic example like water. So now what's going to happen is these negatively charged things are going to gravitate towards these protons. Okay, so as you see all these dipoles I'm drawing, so, okay, because of the acidity of these reagents, they solvate this very well, making that hydroxide really water, and water is no longer that amazing nucleophile that we saw before, because amazing nucleophiles have these full negative charges on them. When they don't have that full negative charge, they become like a weaker nucleophile. Does that make sense?
Yeah, thank you.
Okay, cool. Yeah, I hope that makes sense for everybody. Like, it took me forever to figure that out too, like the difference between like what it really did. And the only thing is that if I'm doing Sn2 conditions, which is really dependent on that nucleophile being really strong, I need aprotic conditions because we don't want this. We don't want that to happen. Okay, so that's Sn2. Anybody else have any questions? All right, great. So we're gonna do Sn1 and E1 now. Okay, so Sn1, Sn2, E1, E2. So actually, let me do E2 before we go. So E2. So we just did Sn2, and now we're doing E2. Okay, so E2 stands for elimination 2, so bimolecular elimination. Bimolecular elimination. So you can kind of rationalize these same exact things happening here. Is that the elimination reaction that we're going to see is dependent on two things. Bimolecular. So the rate law is directly dependent on two things. Okay. And for E2 conditions to happen, we need a base that is not a nucleophile. Okay. Specifically, what do I mean by that? What we're going to call these are bulky bases. Bulky bases, sometimes they're referred to as non-nucleophilic bases. Okay, so what is a non-nucleophilic base? Guys, give me 1 second. I think someone's knocking at my door. All right, so these bases that are not going to act as nucleophiles are bulky bases, okay? So they are non-nucleophilic bases. So what do they look like? So one example we have is tert-butanol, okay? So, or tert-butoxide, I should say. So tert-butoxide has this tert-butyl group, okay? And it has this O, okay? And because of this branching that we have over here, this really bulky alkyl chain, so H3C, H3C, all these methyl groups, it kind of slows down that nucleophile. So, in comparison, maybe like methanol. Methanol would definitely be, slightly nucleophilic, because, you know, it doesn't have as many, you know, substituents as, you know, this butanol or tert-butoxide anion. So sometimes you see this abbreviated as T-BUO-. Sometimes you'll see it, you know, with the other ion, you know, spectator ion associated. So tert-butoxide with sodium, okay, you know, or potassium, anything like that. So that would be an example of a non-nucleophilic base. It is so bulky that this oxygen isn't a nucleophile. So maybe you guys aren't rationalizing why. And I always use the example of a track runner. So I did track in high school, and any of you guys that did track as well, that did like any sort of strength training, would have had parachutes like on your, like they have these parachutes that you can strap yourself onto, and you're supposed to run, you know, like 100 meters, and that parachute is supposed to give you some sort of resistance, which, you know, makes you work even harder to get there. So that's kind of what I view these bulky substituents as. They're called bulky bases or non-nucleophilic bases because all of this extra weight, kind of like that parachute, is holding you back, and it's not allowing these electrons to, you know, attack, you know, an electron deficient center as well as, you know, maybe this methoxide anion would. Does that kind of make sense for you guys? You want like basically a runner or a bullet, you know, something that is really tiny, fast, can move through the air. You don't want any sort of resistance or kind of big, bulky groups, okay? So another example would be LDA. So tert-butoxide is kind of like the most common one in Orgo 1, but the other one is LDA. So it stands for, I think it's lithium diisobutyl amide, something like that. The LDA is the other one. So I know it kind of looks like this, I believe, and LDA, lithium diiso, whatever. I think it's that, if I remember. Lithium diiso. Whatever. Okay, so it's something like this. And you can tell it's the exact same situation going on. These extensive isopropyl, these extensive, you know, carbon chains are limiting how fast this nucleophile can essentially like react or run to that carbon. And because of how extensively branched it is, it can't necessarily react like in a nucleophilic substitution reaction. But what it could do is remove a proton from a very sterically unhindered position and eliminate. So that kind of resembles what we saw earlier. So it couldn't do this because it's too heavy or too bulky to do this nucleophilic addition. But what it could do is something maybe like this, removing a proton that's far away from that center and then fixing that deficiency. Okay, so essentially what it is we have an example like this. Same exact kind of situation going on. So let me do like a bromine up here, and let me subject this to LDA conditions. Okay, so what is LDA? So LDA is this reagent over here, and we know this is secondary, so we're not really sure what it's going to go through, but LDA is a big sign that we're going to do an elimination. It's Sn2 for this case, it's E2 for this case because we're not using a nucleophile, we're using this bulky base, so it loses its nucleophilic properties. So the only thing we can do is take this proton, and I'm going to draw LDA in. I think it's this. Okay? And this LDA is going to act as a non-nucleophilic base, take off that proton, push in the electrons there, and that bromine leaves. Okay, so the resulting structure is this, I believe. Yes, is that. Okay, so it's E2, it's a concerted mechanism because it requires two starting materials, okay, and you're doing the elimination product. You're not adding into the deficiency. You're deprotonating next door. Okay, do you guys understand the difference between Sn2 and E2? Very similar, it's just you lose the nucleophilic properties, and there's only two real reagents you can do with that. Or I could draw anything, like I could give you on the test, like, you know, something that looked crazy like that, and you should know that this is so bulky and so heavy, and that it's not going to be a nucleophile, but it could be a base. All right, any questions?
So practically the difference between nucleophiles and like bases, the bases always attack like a proton, and
Correct.
then the nucleophiles can either attack a proton or go to like, is it mainly carbon?
Yeah, so yeah, we're only dealing with carbon chemistry, yeah. So it's always going to be a carbon that has a substituent, yeah.
Okay, and it's because usually it's a dipole.
The dipole, what do you mean by that?
With like the leaving group.
Yeah.
Dipole.
Yeah, exactly. So there is always a dipole kind of with a leaving group. and that's why that carbon is reactive. Yeah, that's why you're going to have these reactions. So yeah, that's good.
Okay, thank you.
Yep. Anybody else want clarification on anything? All right, great. So now we're going to do Sn1 and E1. So that's Sn2 and E2. So I know it's a lot of info, but I think it's good talking about it like this first. Okay, Sn1 and E1, and we're going to talk about them, you know, in tandem, essentially. Sn1 and E1. So the last half of this. So what's Sn1 and E1 condition? So this means, you know, unimolecular. So now we're not bimolecular. Unimolecular, nucleophilic substitution. So an example would be, you know, and before we were dealing with, you know, primary, you know, leaving groups or primary carbons, now we could deal with something like this. So let me do, I'm just making this up as we go. And let me do maybe, so let's just do, let me make a good leaving group here. Okay, something like that. Let's just say that. Ammonia, positively charged, you know, any charged, you know, substituent indicates that it's a good leaving group. It's unstable the way that it is and would like to leave. So, you know, reaction conditions maybe would be something like this. And we'll do that example. Okay, so this is something that we saw in the beginning. So how do I know this is going to go through an Sn1 pathway? So for starters, we don't have a nucleophile that is really, really strong, okay? So weaker nucleophiles. So weaker nucleophiles, for starters. How do I know it's weaker? It has no negative charge, so no negative charge. So if it has a complete negative charge on it, so like sodium azide or like sodium hydroxide, like that has a full negative charge on the oxygen atoms. But methanol or water or things like that, they don't have a full negative charge. They have slight negative charges due to their dipole moments, but not complete localized negative charges. So that's why they're not as strong, so weaker nucleophile. Also, you're typically gonna have a polar protic solvent. And we know what polar protic solvents do. And polar protic solvents decrease the nucleophilicity. So let's say we don't even necessarily have a weak nucleophile. Let's say we have like an O- thing, but we have a polar protic solvent. That polar protic solvent is going to protonate that negative charge. So what I'm talking about is essentially like this. Is going to, if I had hydroxide, like sodium hydroxide, and I subjected it to a polar protic solvent like methanol, it's going to grab that proton and become water, which makes it weaker. So we typically have polar protic solvents, but you know, in this case, methanol is going to act as both my nucleophile and my solvent. That's just common. You know, when we have waters or alcohols, that's a typical solvent in orgo. So essentially, these are the differences. We have a weaker nucleophile instead of a strong one, and we have a polar protic solvent instead of a weaker one. In addition, before we were talking about sterically unhindered centers, where now we're going to be talking about sterically hindered centers. Okay, this is what we're focusing on, centers. Okay, so now it's tertiary. It's not primary or secondary, it's tertiary. So it's unimolecular in the sense that the mechanistic rate determining step is dependent on that leaving group just leaving on its own. So there is no other, we don't need methanol to be present for that to happen. So the rate law is really equal to some sort of rate constant K times the concentration of that starting material, which would be this protonated ammonia alkyl group. And it's to the first power because it's unimolecular. It's just dependent on that, okay? So essentially the result of that gives you an intermediate, okay? So we get this tertiary carbocation, and all of the things we've talked about before in terms of, you know, rearrangements are possible because we're going through this. So something to remember is rearrangements are definitely possible. Okay, and then now it makes sense what the next mechanistic steps are going to be. So that lone pair on that oxygen is going to attack that carbocation, and you're going to be left with this, you know, protonated ethoxy group. And then you can just assume, you know, there's excess solvent, and that's going to just deprotonate that last proton to form that ether. Okay, so that is the Sn1 pathway. So we promoted an Sn1 pathway by making the alkyl, you know, starting material very substituted. We decreased the nucleophilic properties of our reagent. by reducing, there's no negative charge there. And we're also ensuring that that nucleophile is weak by using a polar protic solvent like water or acetic acid, you know, in this case, it was methanol, okay? And I think the difference before, let me flip, I guess, back to the other page. Difference before with Sn2, which was here, was you can see that we had a concerted mechanism. We had 2 arrows at once, where now we only have 1 arrow as my rate determining step. Okay, so that's what Sn1 means versus Sn2. But with the Sn1 product, you might have looked right back to here and asked yourself, wait, earlier today, I saw Stephen do this, where we saw that methanol coming in an attack, but that methanol was just as likely to deprotonate that proton, donate electron density into, you know, that carbon deficiency and form an alkene. So this looks like the elimination product as well. So which one is it? Well, actually, they happen at the same time. You can't argue because, you know, since we say that nucleophilicity parallels basicity, I'll write that kind of over here. Nucleophilicity parallels basicity. So this is a weak nucleophile. It is also a weak base. So that same methanol that we saw can remove this proton and donate the electron density into the ring to form the alkene that looks like that. Or I could have decided to remove from another adjacent position. It's beta because this would be the beta carbon. With the alpha carbon is the one that bears the carbocation. The beta carbon is the one that's once removed with all these beta protons. So we have 2 different beta protons. Actually, we have 3 different beta protons to choose from. So we could have, you know, chosen this mechanistic pathway and formed this alkene. So, okay. So which one is it? Is it the geminal di-substituted alkene that forms, or is it the tri-substituted alkene that's going to form? Well, if you said the tri-substituted alkene, you're right, because this is the more substituted alkene, which means it's more stable thermodynamically. And this is going to be specifically called the Zaitsev product. Zaitsev product. So it's this famous chemist that just discovered the Zaitsev product, and you know, this guy discovered the Hofmann product. So Hofmann just means the less substituted, you know, alkene of this elimination reaction, and Zaitsev, you know, refers to this more substituted position of that elimination product. Okay, so typically, you know, if I were to say predict the major products of this reaction, you would have to draw 2 things. You would have to draw the, you know, nucleophilic substitution product, and you would have to draw the Zaitsev major product. Okay, so those would be my 2 major products. So the difference is Sn2 and E2 are in competition with one another. That's why we talked about them first. You know, which one is the difference? So let's kind of recap all that. So Sn2 conditions versus E2 conditions were the exact same thing, except the only thing we changed was the degree of strength of our nucleophile. We had the same kind of, you know, I guess starting material, I mean substitution, where this was a primary, this was a secondary, they're both like not as substituted. Okay, but the only difference was that this azide has a negative charge, and this, you know, these bases were Lda and terbutoxate, which were really bulky and only promoted the E2 product. Okay, with Sn1 and E1, every time you have an Sn1 pathway, you're going to have an E1 pathway. So we're going to form this Zaitsev product, okay, because it's the more stable position, and we also form this nucleophilic substitution product. And we deal with more sterically hindered carbons, and we also deal with weaker nucleophiles and polar protic solvents. All right, everyone take a breath to digest that. I know that was a lot of information. So some other things I want to talk about, some key features of E2. All right, I swear we'll wrap up with all that stuff, E2. Okay, so something specifically that needs to happen with E2, and I'm going to give you guys this example. Give you guys this specific example I want to talk about is this guy. So I'm going to show this product. So, okay, and we are going to do these reagents. So it's O minus Okay, so if you guys are following along in the student workbook, I am on page 107, and I'm looking specifically at number 10. Okay, so let's read this. So recall that beta elimination. This is a really good question. Like I wrote this last summer, and I was like, this is really good for teaching the specific, I guess, paradox that we have going on here. So recall that beta elimination can be regioselective in that the major Zaitsev product and a minor Hofmann product typically form. We just talked about that. Look carefully at the experimental percentages below and explain in this scenario why we got the percentages that we did. So we know it's typical for the Zaitsev major product to form, but in this specific reaction, we have 0% abundance. That's really bizarre. And here, the Hofmann product is almost exclusively formed, so I'm missing something. Why is this Hofmann product forming? So first of all, let's kind of like look at the reaction going on here. We know it's beta elimination because we have a really good leaving group. You know, this whole group, once it leaves, is resonance stabilized. If it has a negative charge, it can resonate. Okay, so it's resonance stabilized. So we have a secondary, which is, you know, decently, you know, unsubstituted, and we have this nucleophile that has a full negative charge, so I would think it's strong nucleophile. But what do all of these carbons do? This CH2,3, that's a 4-carbon chain, so that's gonna really, it's like 1, 2, 3, 4, really long and bulky. So this is not nucleophilic. This is actually a non-nucleophilic base because of how big it is. And non-nucleophilic bases are going to do the E2 mechanistic pathway, where they're going to remove a proton from the beta carbon and facilitate the removal of that leaving group. So we have two positions we can look at. So I'm going to draw these in right here. So we have the less sterically hindered position with these two protons, and then we have the more sterically hindered position with that hydrogen on a dash. Okay, so we're getting the situation. There's really two reasons we can rationalize this. So this is a non-nucleophilic base, and the reason why this reaction is forming the Hofmann product is the proton that is to be eliminated has to be in a specific orbital arrangement. We're not going to talk about the orbital specifically, but it has to be in some sort of configuration called the anti-coplanar configuration. So what does that mean? I'm going to draw the chair conformer. I know you guys hate me. This is the only time I said you guys had to draw chair conformers one more time in Orgo 1. And it was this specific example, if you guys remember me saying that. So if I want to draw the chair conformer for that, I'm going to do, you know, maybe do, you know, the one going up. So 1, 2, 3, 4, 5, 6. Okay, so we're here. And, you know, let me call that carbon 1. So if that's the case, carbon 1 would be, you know, equatorial, you know, for this group. Okay, carbon 2, you know, this proton would be down, you know, there would also be a proton in here, and then on carbon 6, that should be, this is up, that would be down. So, you know, that ethyl group is, the isopropyl group is down, and that proton is in. Okay, so that's one chair. And let me draw the other chair, because maybe that could also give me some insights. So that's 1 and that's 4. So 1 now has an axial down. Okay, and 2 is right here, so it's axial up. Okay, and then 6 is now axial up for that isopropyl group, and then we have the proton here. Okay, so this is the chair conformer I really want. You want to draw a chair conformer where your leaving group is axial. So my leaving group equals axial. So this is the chair conformer I want to focus my attention on. Okay, so essentially, let's just figure out what's happening. Why does it have to be anticoplanar? Well, this base, okay, is going to remove this proton because the orbital arrangement is perfect for where those electrons can go into here and that can leave. I think I got a question in here. What just happened? If the isotope was on a wedge, how could it be down? Down, up, down, down, up, down, up, down, up. Yeah, I'm going really fast. You're so right, Farah. I am so happy you were so keen to seeing that. That should be up. And then this should be equatorial. Thank you for that. I really appreciate it. I'm going so fast. Okay. So, this is so ugly now. So essentially what happens is that this proton is able to be removed, thrown down like that, and then kicked off. So this orbital arrangement where it's like this is axial up and this is axial down is perfect for, you know, this base to remove all these things. So anti-coplanar configuration is why we're getting this Hofmann product, okay? This less sterically hindered product, because that proton is in the proper orientation for this to be deprotonated. So the chair conformer is a really long way to do that. For a shortcut, and I'm sure you guys are all gonna do this as soon as I say it to you guys, is that when you are looking at the leaving group, look at your 2 beta positions, here and here. Look for a proton that is on the opposite configuration that that leaving group is. So if the leaving group is on a dash, your next door position has to have a proton on a wedge. Here, since carbon 6 doesn't have it, you can't do elimination on that side. But here, since carbon 2 can, you can do elimination on that side, okay? So you need this anti-coplanar configuration, and you only got that at that position over here. That's why we got the Hofmann product. If you switch this around, so now if I had that same starting material, and I had that isopropyl group on a dash, now that proton is on a wedge. And I would choose to form the Zaitsev product from that because we would form a more substituted alkene. Do you guys understand that? So that's just a little bit more specific on E2 reactions. And this question kind of is a really good example of it. All right. So what time is it right now? Let's see, we're at 3:55. I'm going to let you all leave and digest that because that was a lot. Let's do on Wednesday, we're gonna do practice identifying all of these together. So I'm just gonna like mix all these Sn1 E1s, Sn2 E2s together, and we're gonna do Kahoot on Wednesday, and we're gonna just show a whole bunch of, you know, reagent examples, and you need to tell me which pathways they're gonna go under, okay? So look forward to doing that on Wednesday, and I'll see you guys then.